Every picture you've ever seen of the Sun was taken from almost exactly the same place. We orbit around its middle, staring at its waistline, catching it face-on like a portrait subject who never turns their head. For 400 years, since the first telescopes tilted upward, no one had ever looked down on the top of the Sun or up at the bottom of it. Then, in June 2025, a small group of researchers gathered in a dim control room and pulled up an image nobody in human history had ever seen. It was the Sun's south pole, sharp and real, sent home from a spacecraft that had climbed somewhere no mission had gone before. On the screen sat a magnetic map of that pole, and the room went quiet. Not the good kind of quiet. The colors on it were tangled where they should have been clean, mixed where the textbooks said they'd be uniform. North and south polarity, positive and negative, sat crowded together in the same patch of star. Someone leaned closer. Nobody spoke. The data was clean, the instrument was working, and the picture still looked like it couldn't possibly be right. To understand why that image broke a 400-year streak, you first have to grasp what no telescope has ever been allowed to show. Think about how much of the solar system we've already charted. We've mapped the canyons of Mars, counted craters on Mercury, and traced the frozen plains of Pluto in enough detail to name individual ice mountains, and Pluto sits nearly 5 billion kilometers away. We've flown past the rings of Saturn, dropped a probe into the crushing clouds of Jupiter, and photographed a comet from close enough to see boulders on its surface. Our reach is genuinely absurd when you list it out. And yet the single most studied object in all of astronomy, the star that anchors everything, has two regions no human eye or camera had ever properly seen. Not the surface we squint at every day, the very top of the Sun and the very bottom. Every image you've grown up with, every textbook diagram, every solar flare caught on film, was shot from roughly the same angle. We've watched the Sun for centuries, but always from around its waistline, staring at the equator like spectators locked into one seat. The poles stayed hidden. We could infer them, model them, guess at what churned up there, but a real look straight down onto the top of the Sun simply didn't exist. The reason for that gap isn't distance or technology, it's the shape of the ground we stand on. Picture the whole solar system laid out on a table. The planets don't scatter through space like bees around a hive. They ride an almost perfectly flat sheet, tilted by only a few degrees from one another, all circling the Sun's middle. Earth sits on that sheet. So does every telescope we've ever pointed at the Sun, every probe we've launched, every satellite that photographs it around the clock. We orbit within about 7 degrees of the Sun's equator, which means we're always looking at it edge-on, from the side, like reading a coin by staring at its rim. That flatness isn't an accident, it's a leftover from the disk of gas and dust the Sun and planets formed out of 4.6 billion years ago. Everything spun up in the same plane, and it kept spinning there. So the map we drew of the Sun is really a map of one thin band around its waist, repeated over and over from slightly different angles. For centuries, nobody had a reason to leave that plane. It would take enormous energy, and the view down there seemed like more of the same. But the equator was never the whole story. Two narrow regions stayed hidden in that geometry, and they may quietly run the entire solar system. Picture the Sun as a globe, and then trace your finger to the very top and the very bottom. Those two spots, the North and South poles, are the least photographed real estate anywhere in the solar system. Every telescope, every probe, every school poster shows you the same thing, the belly of the star, the equator turned toward us. The reason is pure geometry. Earth sits almost dead level with the Sun's equator, off by about 7 degrees, so we spend our whole lives looking at its waistline. The poles hover at the edge of the disk, smeared and foreshortened, a sliver glimpsed at a brutal angle. It's like trying to study the summit of a mountain while lying flat on the plain beside it. And here's what makes that gap sting. The surface we can see is not uniform. The magnetic field near the equator behaves one way, and up at those caps, the physics seems to change entirely. The field lines, the rotation, the way material moves. Something up there doesn't match the rest of the star. We're going to hold back exactly how strange it gets, because the answer is worth the wait. For decades, scientists suspected those caps did something violent, but suspicion isn't a photograph. Think about how much of the sun we've actually mapped. We've traced its equator in fine detail, timed its spots, measured its light down to fractions of a percent. Yet the two regions that may drive its whole magnetic personality have stayed in shadow, hidden by simple geometry. The poles aren't just unphotographed, they're the part of the star we understand least, and there's growing evidence they set the rhythm for everything else. Whatever happens at the top and bottom of the sun seems to leak outward, shaping the weather across the entire solar system. And that weather doesn't stay 93 million miles away, it travels. When the sun throws its worst at us, the trigger often traces back to processes near those caps, the ones no camera had ever seen clearly. A star this close, this studied, and its most consequential real estate was a blank spot on the map. That blank spot matters because storms born up there can reach across the void and touch the machines we depend on. The satellites tracking your location, the grids humming behind your walls, the signals threading through orbit. All of it sits downstream of a region we could barely glimpse. Everything you rely on in orbit may depend on what's churning at those poles. So here's the question that's easy to say and hard to answer. What sits directly above the sun's north pole and directly below its south? Not off to the side where we usually watch, but straight over the top and straight under the bottom. Every image you've ever seen of the sun looks at it from roughly the same angle. We orbit near its equator, so we see the middle, the belt where sunspots crowd and flares erupt. The poles hide at the edges of that view, squashed and foreshortened, curving away where our cameras lose the geometry. And there's reason to think the poles aren't just hard to see, they might behave differently. The magnetic field could open up there instead of looping back down. The wind streaming off them might blow faster, colder, cleaner than the gusts we measure at the equator. If that's true, then the pieces we've been missing sit exactly where we've never looked. The engine that drives the whole cycle, the flips, the storms, could be turning in a place permanently at the edge of our frame. For decades, we simply worked around it, mapping a sphere from a single latitude and hoping the rest matched. It doesn't take long to realize how badly you want to climb up and look down. The first attempt to look cost a spacecraft a detour past Jupiter just to get into position. So look again at that image from 2025, the first clear view down onto the sun's south pole. If our textbook picture held, you'd expect something calm and orderly, a single magnetic polarity spread evenly across the cap, like the clean south end of a bar magnet. That's what a stable pole is supposed to look like. That's not what the data showed. Instead of one tidy sign of magnetism, the instruments picked up both polarities tangled together across the same region, north and south, crowded into a patch that should have belonged to just one. Positive and negative field, side by side, where the model said there could only be one. Picture a compass needle that can't decide which way to point, twitching between directions because the ground beneath it is pulling two ways at once. That's roughly what the sun's pole was doing, magnetically speaking, in a place we'd assumed was the quietest real estate on the whole star. For a body we've watched for 400 years, that's a strange thing to finally see up close. The pole wasn't settled. It wasn't the fixed anchor the diagrams promised. And the more the team looked, the clearer it became that this wasn't noise in the signal or a glitch in a brand new camera. That chaos wasn't a malfunction. It was the sun caught in the middle of something. Think about what that actually means. For a process to be caught in the middle, you have to be pointed at the right spot at the right instant, with a camera good enough to trust. Miss the window by a few weeks and you'd see the aftermath, or nothing at all. This wasn't a snapshot of the sun sitting still. It was a snapshot of the sun changing. And that distinction is everything. Every diagram in every textbook shows the sun as a finished thing, a steady lamp with fixed ends and a tidy field wrapped around it. But the readings coming back described something restless, mid-motion, halfway between one state and another. The instruments hadn't photographed a fact, they'd photographed a transition. For decades, that transition existed only on paper. It lived in equations and simulations, in the confident predictions of people who had never actually seen it happen. They knew it should occur. They could tell you roughly when. What nobody had was a direct look at the machinery while it was still moving, still rearranging itself, still undecided. Now something was staring straight at it. The chaos in the data wasn't a flaw to be cleaned up, it was the event itself, unfolding in real time. And it had been building toward this moment for over half a century of failed attempts. So let's fix the moment in time. February 2020. A spacecraft roughly the size of a van lifted off from Cape Canaveral, and the orbit it was chasing had never been attempted before. It wasn't built to circle the sun the way every probe had for 60 years. This one was designed to climb, to break free of the flat lane every planet and every earlier mission had been trapped in, and to lift its whole viewpoint out of that lane entirely. That maneuver alone took years and borrowed the gravity of another world to pull it off. By the time it reached its perch, it was looking down on our star from an angle no camera, no telescope, no human eye had ever held. In June 2025, the images came back, and they showed a region of the sun that had stayed hidden through every observation we'd ever made, across every century we'd been watching. We're going to get to what that region looks like and why it rewrites part of how the sun actually works. But an image only means something if you understand what came before it. So to feel the weight of that image, rewind past the probe, past the plane, to how we ever thought we understood the sun at all. Go back to 1610. Galileo tilts a crude telescope toward the sun, sketches dark specks crawling across its face, and starts a habit that never really stopped. For 4 centuries after that, almost every serious look at the sun came from roughly the same place, a thin slice of space near the plane where Earth and the other planets orbit. And the view from there is generous. We tracked sunspots drifting from one edge to the other. We timed how long they took, worked out that the sun spins, and watched those spots come and go on a rhythm we could set a calendar by. Telescopes sharpened. Then came satellites parked above the atmosphere, staring without a single cloud in the way, feeding us a constant stream of the sun's turning face in wavelengths our eyes can't even catch. By any honest measure, it felt like a solved picture. We had the spin, the cycles, the storms, the churn. Centuries of patient watching had turned a mysterious disk into something we could chart and predict, a star we thought we knew from top to bottom. But every one of those instruments, from Galileo's lens to the newest orbiting observatory, sat in almost the same band of sky. We were all looking from the equator's level. That confidence was built on a view that quietly ignored a third of the star. Step outside on a clear morning, and the sun does exactly what it's always done. It clears the horizon, climbs, warms the back of your neck, and slides down the far side of the sky. Same arc yesterday, same arc tomorrow. That reliability is the whole reason we can set clocks and plant crops by it. Up close, it's a sphere of glowing plasma about 1.4 million kilometers across, so wide you could line up 109 Earths across its face. Its surface, the photosphere, simmers at roughly 5,500 degrees Celsius. It looks smooth from here, a clean yellow-white disk you're told never to stare at. And for most of human history, that was the sun, a dependable lamp, a thing that rose and set with no drama you could see with the naked eye. Steady, bright, finished. But steadiness is a story the surface tells. What reaches your eyes is just the top layer, the light that finally escaped after a long climb from deep inside. The glow is real, and it is also a lid. That calm you feel on your skin is only skin deep. Beneath that calm surface runs a machine no one could see turning. Start with what the sun is actually made of. There's no rock down there, no crust, no solid ground to stand on. It's gas that got so hot its atoms broke apart, electrons ripped loose from their nuclei. That state has a name. We call it plasma. And plasma doesn't just sit there. At around 5,500 degrees Celsius on the visible surface and millions of degrees in the core, the whole thing churns. Hot material rises, cools, and sinks back down, over and over, like a pot of water that never stops boiling. The surface you see is the top of that motion, granules the size of Texas bubbling up and fading in minutes. Here's what changes everything. When you tear electrons off atoms, you get charged particles, and charged particles carry electric currents. Currents make magnetic fields. So the sun isn't just a hot ball of gas. It's a hot ball of gas threaded through with magnetism, and that magnetism pushes back. On Earth, gravity runs the show. Up on the sun's surface, the magnetic fields get strong enough to lift and hold plasma against the pull of a star. Loops arc up. Material hangs suspended, where it has no business hanging. Magnetism, it turns out, is the whole story, and it doesn't stay put. Long before anyone understood magnetism, people were just watching the spots. Chinese astronomers noted dark patches on the sun with the naked eye more than 2,000 years ago, glimpsed through haze and dust storms. They didn't know what they were looking at. They wrote it down anyway. Then in 1610, telescopes turned upward, and the spots became a habit. Galileo sketched them drifting across the disk. Thomas Harriot did the same. Night after night, day after day, observers penciled little dark islands onto paper and dated every page. For centuries, it stayed a quiet, patient chore. Astronomers counted, tallied, and filed the numbers away, not sure they added up to anything. Some years, the sun was freckled with dozens of spots. Other years, its face went almost blank, and the counters kept counting through the empty stretches too. It was a German pharmacist named Heinrich Schwabe who finally caught the pattern. Starting in 1826, he watched the sun nearly every clear day for 17 years, hunting for something else entirely. What he found instead was a rhythm. The spots swelled in number, faded away, and swelled again, rising and falling like a slow tide. Those dark blemishes were keeping time to a clock nobody had decoded. That clock, once someone finally read it, turned out to run on a roughly 11-year beat. Count from one quiet stretch to the next, and you land almost exactly a decade apart, give or take a year. The sun swings from calm to frenzied and back again, over and over, and it's been keeping this schedule for as long as we've watched. At the low point, called solar minimum, the face of the sun can go days with barely a spot on it. Then the count starts creeping up. A few spots, then dozens, then whole clusters crowding the surface until the star reaches solar maximum and its skin is freckled with dark blemishes. And this isn't just about spots you can see. As the count climbs, so does everything else. More flares, more eruptions, more energy hurled off into space. The whole star seems to wind itself tighter. Hold that tension, then slowly let it go. Astronomers have now traced these cycles back through more than 24 numbered rounds of rise and fall. It's the closest thing the sun has to a heartbeat, steady enough to predict, strange enough that we still argue about what drives it. But hidden inside that rhythm is the real surprise. At the top of every cycle, something drastic happens that most people have never heard of. Every 11 years, at the peak of the sunspot cycle, the sun's magnetic field completely reverses. What was the north magnetic pole becomes the south. What was south becomes north. The entire star flips its polarity. This isn't a metaphor or a gradual drift. The field lines that thread through the sun's atmosphere, that shape the corona and drive the solar wind, reconfigure themselves. Within a span of months, the swap is complete, and the sun emerges with its magnetic skeleton inverted. We've watched this happen in 1980, 1991, 2001, 2013. Each time the reversal marks solar maximum, the moment when the sun is most active, most unstable, covered in spots. Then the cycle starts over, counting down 11 years to the next flip. But here's the problem. We measure that reversal from Earth, watching how the field behaves at the equator, inferring what must be happening at the poles. We've never seen the poles themselves go through it. We don't know what the flip actually looks like up there, where it begins. Remember that flip? The climax of this story lives inside it. The sun isn't just sitting there glowing, it's leaking. Every second, roughly 1 million tons of its own material tears free and rushes outward into space. We call that escaping stream the solar wind. This isn't a gentle breeze. It's a flood of charged particles, mostly protons and electrons, ripped loose from the sun's outer layers and flung across the solar system at hundreds of kilometers per second. It doesn't stop at Mercury or Mars. It keeps going, past Jupiter, past Neptune, filling a bubble far bigger than the planets themselves. Earth sits inside that wind right now. It's been blowing against our planet for billions of years, and our magnetic field bends it around us like a stone splitting a river. When it gusts hard, we get auroras. When it really surges, satellites stagger and power grids feel the strain. For decades, we pictured that wind as one steady thing, pouring out in every direction, the same in all of them, a star exhaling evenly on all sides. It's a clean idea, and it's wrong. That wind doesn't blow the same everywhere, and where it changes points straight up and down. Follow that wind outward, and it keeps going. Past Earth, past Mars, past Jupiter and Saturn, it just keeps flowing, thinning as it spreads, but never really stopping. It carves out a region of space that belongs to the sun and nothing else. That region has a name. It's called the heliosphere, a colossal bubble blown by the solar wind, and every planet you know sits deep inside it. The edge of it is somewhere past Pluto, more than 100 times farther from the sun than we are. We only have a rough sense of its shape because it took us decades to reach the boundary. The Voyager probes launched in 1977, and they didn't cross out of that bubble until 2012 and 2018, after flying for 35 years or more. At the edge, the solar wind slams into the thin gas between the stars and finally slows to a crawl. So this isn't a gentle glow around a star. It's a pressurized bubble hundreds of astronomical units across, held open by particles streaming off the surface at hundreds of kilometers per second. And here's what stayed unresolved for years. The strongest gusts filling that bubble had a source no one had confirmed. Now walk toward the sun for a second. The surface, the part we see, sits around 5,500 degrees Celsius. That's hot enough to boil any metal you could name, hot enough to glow that familiar yellow-white. Then you climb higher, away from that surface, out into the thin outer atmosphere we call the corona. Everything you know about heat says it should get cooler out there. It doesn't. It gets hotter, wildly hotter. The corona runs to 1 million degrees Celsius and beyond, in places pushing past 2 million. So the air above the fire is hundreds of times hotter than the fire itself. Move away from the heat source, and the temperature jumps by a factor of a few hundred. Physicists have a name for how strange that is. It breaks the most basic rule we teach children about heat, that warmth flows from hot things to cold things and fades with distance. Here, the faint outer layer somehow outburns the dense surface underneath it. For decades, nobody could say what pumps that energy up there. Magnetic waves, maybe. Countless tiny explosions, maybe. The clues were tangled in the sun's magnetic field, and that field behaves differently depending on where you stand on the star. The equator tells one story. Whatever heats that corona seemed to leave its clearest fingerprints where we couldn't look. So where does that field come from? It's built inside the sun by an engine scientists call the dynamo. The raw ingredients are simple, hot plasma and motion, but the way they combine turns the sun into a self-sustaining magnet. Down in the sun's interior, plasma isn't just sitting there. It's charged, so when it moves, it drags magnetic field lines along with it. And it moves constantly, rising where it's hot, sinking where it cools, churning like water in a pot that never stops boiling. Here's the twist that makes the whole thing work. The sun doesn't rotate as one solid body. The equator spins around in about 25 days, while the poles take closer to 35. That difference in speed grabs the magnetic field and stretches it, winding it tighter with every rotation, like wrapping a rubber band around a spinning ball. Layer in the rising and sinking plasma, and those stretched field lines get twisted and looped on top of each other, Weak field becomes strong field. Order becomes tangle. The dynamo keeps feeding on the sun's own motion, generating fresh magnetism year after year without ever running down. But a magnetic field this powerful can't just pile up forever in one place. That engine has to dump its old field somewhere, and gravity points the way. So follow the plasma. Down near the sun's equator, the surface material doesn't just sit still, it drifts, slowly, steadily, toward the poles, riding a current scientists call the meridional flow. Think of it as a conveyor belt made of glowing gas, stretching across an entire hemisphere. It's not fast by our standards. The plasma creeps along at maybe 10 to 20 meters per second, a walking pace across a body 1.4 million kilometers wide. A single loop, from equator up to the pole and back down through the interior, can take around 11 to 22 years to complete. And it doesn't travel empty. As that surface flow moves, it drags the tangled remnants of old magnetic field along with it, sweeping up the leftovers from decayed sunspots and carrying that magnetism poleward, bit by bit. The equator hands its worn-out field to the belt, and the belt starts hauling it away. Where does it all end up? The flow keeps pushing toward higher and higher latitudes until the plasma reaches the top of the sun and has nowhere left to go. Everything the conveyor collects gets delivered to one destination, piling up at the roof of the star. Follow that conveyor to the end of the line, and you reach the exact place we'd never seen. Watch the surface long enough, and you'll see it happen every cycle. As the active regions decay, they leave behind a trail of magnetic flux, and that flux doesn't scatter randomly. The circulation drags it upward, streaming out of the sunspot belts and marching steadily toward the poles. Solar physicists have a name for the late stage of this migration. They call it the rush to the poles, and the word rush is earned. In the final years of a cycle, you can track bright magnetic surges climbing past 60 degrees latitude, then 70, closing in on the pole faster than anything else on the star's surface. What arrives up there carries a specific sign. It's the trailing polarity of the old cycle's spots, opposite to whatever polarity has been sitting at that pole for years. So the incoming flux isn't reinforcing what's there, it's crowding in against it, drop after drop, like the wrong charge, stacking up where it doesn't belong. The old field weakens, the new field builds. For a while, the two hold an uneasy balance at the top of the star, the tension climbing with every fresh delivery. And when enough flux arrives, it doesn't just sit there, it overturns everything. Here's where it gets strange. That pile of magnetism sitting at the top of the sun isn't just leftover clutter from the last cycle. It's a seed. The amount of field that gathers at the pole quietly sets the stage for whatever comes next. Solar physicists noticed the pattern decades ago. When the polar field is strong going into a minimum, the following cycle tends to come in loud, with more sunspots, more flares, more of everything. When the polar field is weak, the next cycle arrives muted, sluggish, almost shy. Track it across the record, and the link holds up better than almost anything else we've tried. Sunspot counts, flare rates, the whole tempo of the coming decade, all of it echoes back to how much flux stacked up at the top before the cycle even began. So this one measurement, the strength of the polar field, became the closest thing we had to a crystal ball for the sun. It tells you roughly how rough the next 11 years will be for satellites, power grids, and astronauts, years in advance. And that's the part that should make you uneasy. The single best forecast of future space weather sat in the one spot we were blind to. For as long as we've watched the sun, we've watched it from one seat. Earth rides along a flat track called the ecliptic, a nearly perfect disk that our planet and almost every probe we've ever launched shares. From that seat, the sun sits right in front of us, its equator strung across the middle like a belt. Which means we've spent centuries staring at the sun's waistline, the spots we tracked since Galileo, the flares we timed, the 11-year rhythm we mapped. All of it came from that same side-on angle. We saw the middle in crisp detail, and the top and bottom smeared into nothing. Look toward the poles from here, and the surface tilts away from you, foreshortened, crushed against the edge of the disk. Features stretch and blur. A whole polar cap collapses into a thin, unreadable sliver at the rim. You're trying to study the crown of a head while standing at eye level, forever. And no matter how sharp the telescope, that geometry never budges. A bigger lens can't peer over a curve. To see over that edge, you'd need to do something no rocket alone can manage. So think about what that curve actually does to the view. When you point a telescope at the sun's pole, you're not looking down at it. You're looking almost sideways, skimming across it at a razor angle, catching the very rim of the sphere as it bends away from you. Astronomers call this foreshortening, and it wrecks everything about the picture. Features near the pole get squashed into thin, smeared streaks. A patch of magnetic activity that might sprawl across a wide region gets crushed into a few blurry pixels, stretched flat against the edge of the disk. From Earth, we sit roughly in the sun's equatorial plane, tilted only about 7 degrees off it. That tiny tilt means the poles never rotate into clear view. The best you get is a glancing peek at a slice that's already curving out of sight. So the polar magnetic field, the very thing that drives the whole cycle, showed up only as a faint, warped signal at the limb. Measurements there carried huge uncertainty. You were reading the fine print of the sun through frosted glass, guessing at structure you could barely resolve. For decades, that was the ceiling. The sharpest instruments humanity could build still stared at the poles from the side, catching shapes too distorted to trust. Those distorted glimpses hinted at chaos, but a hint is not a discovery. So here's the uncomfortable part. Almost everything we said about the sun's poles came from math, not eyes. Nobody had ever looked straight down at them. The pictures in the textbooks were reconstructions, built from what we could see near the equator and stretched upward to fill the gap. Scientists fed decades of surface measurements into computer models, then let the equations extrapolate what the top and bottom should look like. The magnetic field lines fanning out from the poles, the speed of the wind pouring off them, the way the whole thing supposedly flipped every 11 years. All of it inferred. All of it a best guess, dressed up as a diagram. And the models were good. They matched the data we had. They predicted the cycles well enough to be useful. They held together for years. That's exactly what makes this uneasy. A theory that works everywhere you can check it starts to feel like fact, even in the one place you've never checked. We were confident about a region no human instrument had ever seen from above. Confident about numbers we'd never measured directly. Confident right up until someone finally went and looked. Because models are only as good as the day something proves them wrong. So why hadn't anyone just flown up there and looked? It comes down to a number, and the number is brutal. Everything you launch from Earth inherits Earth's motion, and Earth is racing around the sun at about 30 kilometers per second, all of it in the flat plane of the ecliptic. To leave that plane and climb over the sun's pole, you can't just nudge sideways. You have to cancel a huge chunk of that sideways speed and redirect it upward. Doing that in one shot means changing your velocity by tens of kilometers per second, an amount engineers call delta V. That figure is the wall. Reaching a steep angle over the poles would demand more delta V than any rocket ever built could deliver, even one throwing away its own payload for fuel. The math isn't close. It's off by a wide margin. Think about it this way. To get out of the plane, you're fighting the entire orbital momentum of a planet, and no chemical engine carries enough propellant to win that fight directly. You'd need a booster the size of the problem itself. For decades, that single number kept the sun's poles off limits, not because nobody wanted the view, but because physics said the fuel didn't exist. Then a few engineers found a loophole hiding in the solar system's own machinery. Rockets couldn't do it, so someone proposed borrowing a planet. For a while, that loophole stayed on paper, and for good reason. Every kilogram you launch has to be lifted out of Earth's gravity, then flung across the plane where the planets ride. To leave that plane and climb over the sun costs even more, and the numbers pile up fast. Think about what a mission like this actually demands. You need a spacecraft that can survive years in deep space, instruments delicate enough to read a magnetic field, yet tough enough to shrug off radiation, and a trajectory no chemical rocket can fly on its own. Each of those problems alone could sink a proposal. And then there's the money. A flagship space mission runs into the hundreds of millions of dollars, sometimes past $1 billion, and it takes a decade or more from sketch to launch. For a target that had waited since Galileo, that's a hard sell to anyone holding the budget. So the poles stayed a blank space on the map, not from lack of curiosity, but because the bill kept coming back too high. Somebody, eventually, had to decide the view was worth every one of those risks. It would take an alliance and a gamble past the largest planet to even try. For 4 centuries, that flat view was enough. From it, we learned the 11-year rhythm of the spots, the great flip of the magnetic field, the steady push of the solar wind out past every planet. We built the models, ran the forecasts, and mostly trusted them. But every one of those numbers came from the same narrow band around the equator. The sun's surface spins fastest there, roughly every 25 days, and slower toward the top and bottom, closer to 35. That difference winds the magnetic field like thread on a spindle, and we could only ever watch the middle of the spool. The engine that drives all of it, the flip, the cycle, the wind, reaches down into regions we had literally never laid eyes on. A whole hemisphere of behavior sat above our line of sight, and another sat below it. We had a confident theory of a star we'd only half seen. So the picture felt finished, and it wasn't. The parts that mattered most for prediction were exactly the parts hidden by the angle. Closing that gap meant leaving the plane entirely, and there was no easy way up. The plan to fix that began with a spacecraft aimed in exactly the wrong direction. Picture the goal for a second. You want to look straight down at the top of the sun, from somewhere high above its north or south pole. Every planet, every moon, nearly every probe we'd ever launched sat in the same flat disk around the sun's middle. To get above that disk, you have to climb out of it. And climbing is the one thing rockets are terrible at once they've left Earth. Here's the maddening part. A spacecraft leaving Earth already carries our planet's sideways motion, about 30 kilometers per second, all of it pointing along that flat plane. To tilt your path up and over the pole, you'd have to cancel a huge chunk of that speed and add a fresh push straight out of the disk. No rocket ever built could carry enough fuel to do it directly. So the engineers did something that looks backwards. Instead of aiming up, or even toward the sun, they pointed their probe outward, away from the warmth, toward the cold giant on the far edge of the inner solar system. They sent it to Jupiter, roughly 800 million kilometers in the wrong direction. It sounds insane until you understand what Jupiter's gravity can do to a trajectory. Jupiter is more than 300 times the mass of Earth. That mass warps the space around it into a deep gravitational well, and anything that falls toward the planet picks up enormous speed on the way in. The trick is that you don't crash into it. You aim to just miss it. As the craft whips past, Jupiter's gravity grabs it and flings it back out. Relative to the planet, the probe leaves at the same speed it arrived. But relative to the Sun, it steals a slice of Jupiter's own orbital motion, and that changes everything about where it can go next. Here's what makes it worth 800 million kilometers in the wrong direction. You can angle that flyby, so the craft isn't just thrown faster, it's thrown sideways, lifted clean out of the flat plane where all the planets circle. No rocket ever built could push a payload that far off the plane on its own fuel. Jupiter does it for free. So the plan was never to fly up. It was to fall outward, borrow the giant's pull, and let physics bend the path toward the poles of the sun. It took decades of orbital math to prove it would even work. One spacecraft was built for exactly this maneuver, and its name meant the Wanderer. Ulysses launched in October 1990, riding the shuttle Discovery into orbit before firing off toward deep space. It was a joint project between the European Space Agency and NASA, a single probe carrying instruments from both sides of the Atlantic. Nothing like it had ever flown, because no mission had ever tried to leave the flat plane where the planets ride. The craft itself was modest, a little over 370 kilograms, spinning slowly to keep itself steady. It didn't carry a camera meant to photograph the sun. Instead, it packed instruments to feel the space around it, to measure magnetic fields, charged particles, and the wind streaming off our star. The plan was patient and strange. Ulysses would fly outward for years, all the way to Jupiter, and use that giant to throw itself onto a path steep enough to climb over the sun's poles. From up there, it could sample regions no probe had ever touched, the high-latitude wind and field that stay hidden from every craft locked to the equator. For the scientists who'd spent years on the orbital math, this was the moment the idea became real hardware moving through the dark. But the payoff was still a long way off. Before it could look down at the sun, it had to survive the trip to Jupiter. Ulysses reached Jupiter in February 1992, after 16 months of coasting outward. It didn't go there to study the planet. It went there to steal a piece of Jupiter's momentum. The physics is almost unfair. A spacecraft falls toward a giant world, whips around it, and leaves with a chunk of the planet's orbital energy stitched into its own path. Jupiter barely notices. Its motion around the sun slows by an amount you'd need a cosmic stopwatch to measure. For Ulysses, that borrowed energy did something no rocket on Earth could manage. It bent the probe hard out of the flat lane every planet travels in and hurled it back toward the sun on a steep, tilted loop. The new orbit was inclined about 80 degrees to the ecliptic, close to a straight up-and-over path across the solar poles. No machine had ever ridden a track like that. Everything we'd sampled of the sun's neighborhood came from that thin, crowded plain near the equator. Now a single spacecraft was falling sideways off the map, aimed at regions nobody had ever touched. The climb was slow and quiet, years of it, edging higher above familiar space. And as it climbed above the plane, its instruments started reading numbers that didn't fit the models. Every probe before Ulysses had lived on the same thin sheet, the ecliptic, the flat disk where the planets orbit and the sun's business seems to happen. That's where the data came from. That's where the maps were drawn. Ulysses was leaving all of it behind, 1 degree at a time. By 1994, it had climbed to latitudes no machine had ever occupied, sailing high over the sun's southern hemisphere. Below it, the equator it had abandoned. Above it, empty sky nobody had sampled. The instruments kept sending back readings, and the readings kept drifting away from what the textbooks predicted. On the plane, the solar wind was a mess. Fast streams and slow streams tangled together, gusting and stalling, colliding into shocks that rattled every detector. Scientists had spent decades treating that chaos as the sun's normal breath, because it was the only breath they'd ever measured. But the numbers coming off Ulysses were getting cleaner as it rose, not messier. The turbulence was thinning out. Something about the high latitudes was different, steadier, stranger, and it was tightening its grip on the data the further the probe went. The higher it climbed, the faster the solar wind screamed past it. Down near the equator, the solar wind ambles along at roughly 400 kilometers per second. Fast by any earthly standard, sure, but for the sun, that's the sluggish setting. That slow stream is what Earth swims in, what every textbook had quietly assumed was the norm across the whole star. But as Ulysses kept climbing, the numbers stopped behaving. The wind wasn't just steadier up there, it was hauling. The speedometer crept up and up, past 500, past 600, and it didn't level off where anyone expected. By the time the probe was staring down over the high latitudes, it was clocking a torrent, moving near 750 kilometers per second, almost double the equatorial crawl, and it held that pace with an eerie consistency, hour after hour, degree after degree of latitude. This wasn't a gust or a flare or some passing storm. It was the baseline. The poles, it turned out, were running a completely different engine than the belt around the middle, blowing out a steady, blistering gale that nobody had ever caught in the act. And that raised the obvious question, the one the data refused to answer on its own. Where does that speed come from? Something at the poles was flinging particles out at nearly twice the expected rate. The answer sits in dark patches on the sun's face, and they're darker for a reason. When you photograph the corona in ultraviolet or X-ray light, most of it glows with hot, trapped gas. But near the poles, huge regions look almost black. Those are coronal holes, and they're not empty. They're just cooler and thinner because the plasma there isn't being held down. Everywhere else on the Sun, the magnetic field loops out and curves back, arcing from one spot to another like a hair clip. That closed shape traps the gas, so it piles up, heats, and shines. A coronal hole is where those loops break the pattern. Instead of arcing back to the surface, the field lines head straight out and keep going, stretching into space without ever returning. So the plasma sitting on top of an open line has nowhere to loop back to. It just streams away, accelerated along that highway with almost nothing to slow it down. That's the launch pad. The fast wind Ulysses measured over the poles was pouring out of these open regions, funneled outward at 750 kilometers per second, while the trapped equatorial gas dribbled out at half that. During solar minimum, the biggest, most stable coronal holes park themselves right over the north and south poles. Those open holes meant the polar magnetism was doing something the rest of the Sun wasn't. Think about what an open field line actually is. Over most of the Sun, magnetism comes in arches. A line pokes out of the surface, bends, and dives right back in somewhere else, trapping the gas between its feet like beads on a wire. At the poles, that geometry breaks. The lines climb out of the surface and just keep going. No return foot, no arch, no cap. They stretch up through the corona and off into the solar system, and nothing pulls them back down. That's the difference the coronal holes were pointing at. An arched line holds its plasma hostage, an open line hands it a straight road out, so the charged gas riding those polar lines doesn't dribble or leak sideways. It runs, and it doesn't stop. Which means the poles aren't sealed at all. They're the one place on the Sun with a door propped permanently open, venting particles outward along field lines that reach past the planets. The north and south caps are quietly bleeding the Sun into space, day after day, no storm required. And once you see the poles that way, the stakes shift. This isn't a small polar detail anymore. If the poles are the escape hatch, then they shape everything downstream of the Sun. So Ulysses climbed to those high latitudes expecting chaos. The models said the polar wind should be patchy, turbulent, streaked with slow and fast currents fighting each other. Instead, the probe found something almost eerily smooth. The fast solar wind poured out at a steady 750 kilometers per second, mile after mile, hour after hour, barely wavering. No tangled mess, just a broad, uniform river of plasma streaming off the top of the star, the same over the South Pole as the models had never quite let anyone picture. The cosmic rays behaved the same way. These are particles born in distant supernovae, and physicists assumed the Sun's magnetic field would funnel them toward the poles in uneven bursts. Ulysses measured a smoother flow than the neat diagrams predicted, as if the Sun's shielding didn't care about latitude the way the math insisted it should. That uniformity should have felt like an answer. It didn't. When the real Sun behaves more simply than your best theory, it means the theory was reaching for structure that isn't there, and you're left holding a map that fits the data for the wrong reasons. Ulysses had felt the poles. It had tasted the wind and counted the particles pouring off them. But one thing Ulysses could not do was the very thing we needed most. Ulysses carried no camera, not a single lens pointed at the Sun, not one imager built to capture those poles it was flying over. In all that engineering, in a probe that had crossed the solar system and climbed out of the ecliptic, there was nothing on board to take a picture. What it did carry were instruments that measured, magnetometers to read the field, detectors to count the charged particles slamming into them, sensors that tallied the speed and density of the wind streaming past. Ulysses was a probe that touched the Sun's environment with its fingertips, reading everything by feel. So we knew the numbers over the poles, we knew how fast the wind blew there, how the magnetic field behaved, how many particles came pouring out of that region. We could describe the poles in tables and graphs and decades of raw data. But describing is not the same as seeing. We never watched a pole rotate beneath us. We never saw the surface, the loops of plasma, the structure of the light. The map stayed blank in the one place it mattered, filled in only with measurements taken in the dark. We had the pulse of the poles without a single portrait to match it. Think about what it means to know something without ever seeing it. Ulysses could count particles streaming past, clock their speed, feel the tug and twist of the magnetic field. It logged temperature, density, the direction of every gust. What it couldn't do was look. It's a strange kind of knowing. Imagine mapping a stranger's face in total darkness, tracing the ridge of a brow, the slope of a cheek, the corner of a mouth. You'd build a real picture in your mind, accurate in its way. You'd still have no idea what the person actually looked like. That was the pole of the sun for years. We had numbers pouring in from 80 degrees of solar latitude, the fast wind clocked near 750 kilometers per second, the field reading steady where models said it should churn. Every value checked out, every value arrived without an image attached. You can graph a magnetic reversal, you can't frame it. The data told us the poles were quieter and faster and cleaner than the equator, and we believed it, because the instruments don't lie. But belief built on touch alone leaves a hunger that measurement never fills. So the numbers sat in the archive, precise and blind, waiting for someone to give them a face. A generation later, engineers set out to bring a camera where Ulysses only groped in the dark. Ulysses wasn't built for a single flyby. The mission plan called for multiple orbits, each one threading over the South Pole, then the North, then back again. The spacecraft would loop through the sun's outer reaches on a 5-year rhythm, crossing the polar zones at different phases of the solar cycle. The first southern pass came in 1994 during solar minimum. The craft swung up through the south in 1995, then down over the North Pole later that year. 5 years later, it returned, and the cycle repeated. By 2001, it had completed a full circuit during solar maximum, when the sun's magnetic field was supposed to be tangled and violent. The instruments logged field strength, wind speed, particle flux. Each pass generated a new column of data, stamped with a date and a latitude. Engineers stacked the passes side by side, looking for patterns. The numbers from the first orbit sat next to the numbers from the second, then the third. Something had shifted. The magnetic topology wasn't identical between visits. The field lines over the South Pole in 1994 pointed one way. By 2001, they'd switched. The same reversal showed up in the north. Comparing those passes hinted that the poles were not fixed. They were mid-flip. Ulysses kept measuring, and the numbers kept sliding. Near the peak of the cycle, the polar magnetic field wasn't just tilting, it was losing strength, dropping toward values the spacecraft had never recorded over either pole. A stable pole should read like a bar magnet, clean and one-directional. What Ulysses felt instead was messier. The field pointing out of the south was fading, and stray patches of the opposite sign were creeping in where they had no business being. That's the signature of a magnet coming undone. The old order at the pole was breaking down, piece by piece, and something new was trying to take its place. The readings couldn't tell you the final state. They only told you the ground was moving. And here's what made it worse. Ulysses had a single instrument feeling the field one point at a time, along one long looping orbit. It couldn't hover over the pole. It couldn't hold still and stare. Each pass was a snapshot years apart, from a spacecraft with no camera pointed at the thing changing. So the clue was undeniable and maddening at once. Something enormous was rearranging itself at the top and bottom of the sun. The field was tearing itself apart, and nobody could watch it happen in real detail. By 2009, Ulysses was running out of the one thing no spacecraft can carry enough of. Its power came from a chunk of plutonium slowly cooling down, and after 18 years, that heat had faded too far to keep the instruments and the fuel lines warm at the same time. Out past Jupiter, sunlight is feeble, so there was no backup, no sunny window to bask in. The choice came down to physics, not budget. Engineers nursed it as long as they could, switching things off in sequence, buying weeks here and days there. But hydrazine freezes near 2 degrees Celsius, and once the heaters couldn't hold that line, the thrusters would cease for good. On June 30th, 2009, they sent the last commands and let it go silent, still looping around the Sun on that steep, tilted orbit. It had circled the poles 3 times across 2 solar cycles, and it left behind numbers nobody had ever measured. Yet the deepest questions stayed open. It felt the field reversing but never pictured it. It sampled the fast wind but couldn't trace it home. Ulysses died, having proven the poles mattered more than anyone expected, and that we still hadn't truly seen them. But the numbers it left behind kept working long after the spacecraft went quiet. For 18 years, Ulysses had streamed back readings from places no probe had touched, 3 full loops over the Sun's poles, and every one of those measurements landed in the hands of people building models of the heliosphere. Before Ulysses, most maps of the solar wind assumed the Sun blew roughly the same in every direction. The data rewrote that. It showed a slow, dense wind hugging the equator and a fast, thin stream pouring off the poles at close to 750 kilometers per second. 2 distinct regimes that models had to be rebuilt to hold. The measurements of cosmic rays sneaking in over the poles reshaped how we understand the bubble the Sun blows around the whole solar system. Its magnetic readings pinned down how the field spreads out into space, feeding equations that still run today. Decades of simulations trace their calibration back to those passes: space weather forecasts, heliosphere shapes, the physics of that fast polar wind. All of it leaned on a single spacecraft that flew where nothing had flown before. And yet, for all it corrected, one thing stayed stubbornly out of reach. Every model it improved sharpened the one question it left unanswered. Here's what Ulysses actually gave us: graphs, field strengths plotted against latitude, wind speeds climbing as it rose, magnetic readings logged second by second as it swept over regions no probe had touched. The poles were charted, in the sense that we had numbers for them. But run your finger across any map of the Sun from that era, and the top and bottom stay empty. We knew the polar wind blew near 750 kilometers per second. We knew the field up there behaved differently. What we didn't have was a single picture. Not one frame showing the pole as a place, only columns of data describing it from the side. That gap sits uneasily in the science. You can measure a thing precisely and still never have looked at it. Ulysses felt the poles the way you'd feel a room in the dark, counting steps, touching walls, never once seeing the shape of it. So the map stayed unfinished. Every improved forecast, every refined model kept circling back to the same void where an image should be. Closing it meant getting somewhere Ulysses never could, tilting a camera down onto the pole and actually watching it churn. Filling that blank would demand a spacecraft tougher than anything sent sunward before. But toughness there means something different than anywhere else in the solar system. Push a probe close enough to look down at a pole, and the numbers stop sounding like engineering and start sounding like a threat. The sunlight isn't just brighter, it piles up fast, and it doesn't ease off the way it does out near Earth. At our distance, the Sun delivers about 1,361 watts on every square meter. Halve that distance and the energy quadruples. Get in tight, within a few solar radii, and the flux climbs into the hundreds of thousands of watts per square meter, hammering the front of anything that dares to sit there. That energy turns into raw temperature. Surfaces facing the Sun at that range can be driven past 1,000 degrees Celsius, hot enough to soften metals and cook electronics into silence in minutes. And heat is only half the assault. The same stretch of space floods a spacecraft with radiation, high-energy particles that chew through circuitry and blind the very sensors sent to sea. So the problem sharpens into something almost contradictory. You need cameras and instruments alive and working, sitting in a place designed to destroy them. To stare at the poles up close, a probe would have to hide behind a shield and still keep watching. Think about what that shield is actually up against. Facing the Sun from close range, the front of a spacecraft can climb past 500 degrees Celsius, hot enough to soften metal and cook electronics into silence. The whole point of the barrier is to swallow that heat before it reaches anything fragile behind it. But a shield that blocks everything blocks the view too. A camera buried in shadow sees nothing. The instruments that need to measure the sun have to somehow face the very thing the shield exists to hide from. You can't just cut a window in the armor, punch a permanent hole, and the heat pours straight through it, funneling hundreds of degrees onto the sensor you were trying to protect. The gap that lets you see is the same gap that kills you. So engineers were stuck between two failures: seal the shield completely and go blind, open it up and burn. Every fix for one problem made the other worse, and there was no obvious place to stand between them. The answer, when it came, was almost stubbornly simple. Instead of a fixed opening, you make the hole temporary. The solution was a set of doors that open onto the sun for only seconds at a time. Picture a spacecraft armored against a furnace, its front face a heat shield built to soak up temperatures near 500 degrees Celsius. Now imagine cutting holes in that armor on purpose. Each opening is tiny, no wider than it needs to be, and each one is a direct line to the fire. Behind the shield sit the cameras and spectrometers, the delicate optics that would cook in an instant if they faced the sun unprotected. So the apertures stay sealed most of the time. When a measurement is needed, a small door slides open, lets the light pour through for a few seconds, then shuts again before the heat can build. Think about what that means. Every single image, every reading of the sun's surface, requires briefly exposing the instrument to a full blast that the rest of the craft spends all its energy hiding from. Observation stopped being a passive act. It became a calculated risk, taken in short bursts, timed to the second. So the mission holds back. It can't stare. It peeks, gathers what it can, and closes the shutter, trading continuous vision for survival. That risky design belonged to a probe already being built in Europe. But before that probe could open its shutter, an older wound in solar physics was still bleeding. The sun's surface sits at about 5,500 degrees Celsius. Climb outward into the corona, that faint halo you see during an eclipse, and the temperature jumps past 1,000,000 degrees. That's backwards. Move away from a fire and you should feel less heat, not more. Yet the corona runs hundreds of times hotter than the surface it floats above, and for decades, nobody could name the source of that energy. The heat has to come from the magnetic field. Twisted, snapping lines dumping energy into thin gas is the leading suspect. But the field doesn't behave the same everywhere across the sun, and the strongest, most tangled structures don't necessarily sit where we'd been watching. The equator gets crowded with sunspots and loops, so that's where the cameras stared. The poles stayed a rumor. And if the magnetic architecture there is different, if the field lines open and reach in ways the equators never do, then the accounting we'd done might be missing its biggest entry. That possibility carried a quiet threat. Every model of coronal heating had been built from an equatorial view, checked against equatorial data, trusted for years. If the corona's furnace is stoked at the poles, we'd been studying the fire from the wrong angle. There was something else buried in the solar wind, and nobody could explain it. When spacecraft measured the magnetic field carried out from the sun, they expected it to point steadily outward, flowing away in a smooth, predictable direction. Instead, the field sometimes snapped completely backward, then flipped forward again, all within seconds or minutes. These reversals came to be called switchbacks, sharp S-shaped kinks in the magnetic field lines, like a garden hose whipping back on itself. Early instruments caught hints of them as far back as the 1990s, but the readings were rare and easy to dismiss. A stray glitch here, a strange spike there, nothing worth losing sleep over. Then Parker's solar probe flew closer to the sun than anything ever had, and the switchbacks were everywhere, not occasional, constant. The field wasn't just kinking now and then, it was folding back on itself again and again, packed into the wind like knots in a rope. Whatever was making them had to be violent, and it had to be happening close to the surface. The smooth, orderly outflow that models assumed simply wasn't there. These magnetic zigzags suggested the sun's field was more restless than any pole model allowed. So NASA sent something in to find out. Parker Solar Probe launched in 2018 with one goal that sounded impossible: get closer to the sun than anything humans had ever built. It carried a heat shield just 11.4 centimeters thick, a slab of carbon composite meant to hold back temperatures over 1,370 degrees Celsius, while the instruments behind it stayed near room temperature. Then, on April 28, 2021, it did the thing physicists had talked about for decades. Parker crossed into the corona itself, the sun's outer atmosphere, and for the first time, a spacecraft was flying inside the star's own crown. It passed below the point where the sun's magnetic grip finally lets go of the plasma, the boundary called the Alfvén surface, roughly 13 million kilometers above the surface. Inside that boundary, Parker flew straight through the switchbacks, sampling the field where it kinks and snaps. It clocked speeds near 587,000 kilometers per hour, fast enough to cross the United States in about half a minute. Nothing made by people had ever been so intimate with a star. But there was a limit built into the whole mission. Parker orbits close to the sun's equator, skimming the waistline of the star. For all its daring, it could touch the sun, but never rise above it to see the poles. Think about what closeness actually buys you. Parker screams through its closest approach at over 430,000 miles per hour, dipping to within 3.8 million miles of the surface, closer than anything humans have ever sent. It samples the corona from the inside, tasting particles that have never touched a spacecraft before. But every one of those record-breaking passes happens over the same stripe of sky. The probe loops around the equatorial belt, the fat middle of the star, staring at the churning surface it knows best. The poles sit off to the side, tilted away, forever at the edge of the frame. So proximity gave us heat and speed and texture, but it couldn't give us the one view that mattered. You can press your face right up against a globe and still never see the top of it if you're standing at the equator. Parker had the reach. It just didn't have the position. And that reframes the entire problem. For decades, the assumption was that if we could only get near enough, the sun would finally give up its secrets. Getting near enough turned out to be the easy part. The missing ingredient wasn't distance to the sun, it was angle. Think about where every spacecraft we've ever launched actually sits. They ride in roughly the same flat sheet the planets trace, a thin disk that wraps around the sun's middle. From that vantage, you can stare at the equator for a lifetime and never once glimpse over the top edge. The sun's poles hide just above and below that plane, tipped out of view like the crown of a head you can only see the sides of. To look down on one, you can't just fly closer. You have to climb, to lift your whole orbit up and out of that shared sheet, until you're staring at the sun from a steep angle no camera has held before. That climb is measured in degrees of tilt, and every single degree is brutally expensive. A spacecraft launched from Earth inherits Earth's motion, and Earth lives in the flat lane. Breaking out of it means fighting the exact momentum that put you in space to begin with. So the whole mission becomes a hunt for angle, not speed, not proximity, just the sheer stubborn geometry of rising above the equator to peer at the top. And earning that tilt would mean years of gravitational bargaining with a neighboring world. The trick sounds almost too simple. You can't just fire a rocket to lift yourself out of the flat plane the planets ride in. That kind of climb costs more fuel than any launcher can carry, because tilting an orbit around the sun means fighting the momentum of the entire solar system. So instead of brute force, you borrow. Every time a spacecraft swings close to a planet, that world's gravity yanks on it, bending the path and handing over a sliver of its own orbital motion. Aim the flyby just right, and the craft climbs a little, tipping its orbit up out of the equator. Venus becomes the perfect partner for this. It sits closer to the sun than Earth, it's massive enough to pull hard, and it comes back around often enough to keep offering repeat encounters. One pass alone barely nudges the angle. But you don't take one pass, you take many, threading the same planet again and again, letting each encounter stack a few degrees of tilt onto the last. It's slow, patient theft, and it demands a craft willing to spend a big chunk of its life just circling, waiting for the next alignment. Each pass by Venus would buy a few more degrees of view, paid for in years. So, say you buy those degrees, and the poles finally swing into view. What are you actually hoping to catch? The dynamo is the engine that flips the sun's magnetic field every 11 years or so, and the polar regions are where the old cycle goes to die, and the new one quietly takes root. Here's the part that keeps the models honest. Magnetic flux from decayed sunspots drifts poleward over years, and it carries the opposite polarity to whatever's already sitting up there. So the old polar field doesn't just fade. It gets slowly cancelled, buried under the arriving flux, until the pole crosses through zero and rebuilds with the reversed sign. That cancellation is the whole hinge of the theory, and nobody has watched it happen from above. We infer it from the side, from field lines projected against the limb, from numbers that get shakier the closer you push toward 90 degrees of latitude. The measurements thin out exactly where the answer lives. And the competing dynamo models disagree most sharply right there about how fast the flux cancels, how deep the rebuilding reaches, whether the timing is clockwork or something looser. The only way to settle it was to watch the poles during the exact moment they reverse. So the timing mattered more than anything, and the sun was already counting down. Every 11 years, its magnetic field builds toward a peak, the point we call solar maximum, and around that peak the poles do something almost impossible to picture. North becomes south, south becomes north. The last flip finished near 2014. That put the next one on a schedule pointing straight at the mid-2020s, with forecasters circling 2025 as the window when activity would crest and the polar fields would collapse towards zero. That collapse is the whole ballgame. The old field has to cancel completely before the new one can lock in with the opposite sign, and nobody could say in advance exactly when the zero crossing would land, or whether north and south would flip together or drift out of step by months. Which is where the dread creeps in. We had a spacecraft climbing higher above the ecliptic every orbit, tilting its view toward latitudes no camera had ever seen head-on, arriving on a clock that overlapped the reversal almost perfectly. Line up the two timelines and the coincidence stops feeling like luck. A mission racing toward the poles might arrive right as the sun turned itself inside out. So why does staring at the poles matter so much? Because the polar field is the seed. The strength of the magnetism piled up at the top and bottom of the sun near the end of one cycle is the single best predictor we have for how strong the next cycle will be. Get a clean read on that number, and the forecast tightens. Right now, we mostly infer it. We watch the field from the side, near the ecliptic, and extrapolate what's happening 60, 70, 80 degrees up. It's a bit like judging the depth of a snowdrift by squinting at it from across the yard. The numbers we plug into cycle models are estimates stacked on estimates. A spacecraft actually tilting toward those latitudes changes the input. Instead of guessing the polar field strength, you'd measure it and feed a real value into the machinery that projects sunspot counts years ahead. That's the payoff nobody's had before. And this isn't an academic exercise. Those forecasts drive real decisions: when to launch satellites, how to shield power grids, whether astronauts stay behind shielding. Getting this measurement wrong has already cost satellites and grids more than most people realize. When the sun throws a tantrum, it doesn't send a warning shot. A coronal mass ejection can hurl 1 billion tons of plasma at us at speeds over 1,000 kilometers per second, and the fastest ones cross the 150 million kilometers to Earth in under a day. What arrives is a wall of charged particles and a magnetic shockwave that our planet was never built to shrug off gently. The damage is brutally physical. High-energy particles punch through satellite electronics, flipping bits and frying circuits that can't be repaired from the ground. In 2022, a relatively mild storm puffed up the upper atmosphere, just enough to drag 38 newly launched Starlink satellites out of orbit before they ever reached their stations. They burned up, tens of millions of dollars gone in days. Down here, the effects ripple through the systems we lean on. GPS signals wander by meters as the ionosphere churns, which is a real problem for aircraft, farm equipment, and anyone drilling a precise hole in the seabed. Radio blackouts swallow communications across whole continents. Currents induced in long power lines can overload transformers, the kind that take months to replace. And for astronauts, it's not an inconvenience, it's a radiation dose. A big flare outside the protection of Earth's magnetic field could deliver enough exposure to threaten a crew's health in a single event, which is why missions have safe zones and why forecasters watch the sun like hawks. Taming those storms starts with reading the poles, the very reading we lacked. Go back to September 1st, 1859. A British astronomer named Richard Carrington was sketching sunspots when a burst of white light flared across his lens, brighter than the surrounding surface, gone in about 5 minutes. He'd just watched a solar flare erupt in real time, the first anyone recorded. What followed arrived roughly 17 hours later, faster than any storm before or since in the records. A cloud of charged particles slammed into Earth's magnetic field and set it ringing. Auroras that normally hug the poles spilled down to the Caribbean, and people in the tropics read newspapers by the glow at midnight. Then the wires started to fail. Telegraph systems across Europe and North America sparked and shorted, some so charged that operators unplugged their batteries and kept sending messages on the current. The storm itself was pumping through the lines. A few offices caught fire. Paper smoldered on desks. In 1859, the telegraph was nearly the whole electrical grid. There were no power stations, no transformers, no satellites overhead, no continents wired into a single network. The damage stayed small because there was so little to damage. That's the part worth sitting with. A storm like that today, unpredicted, could darken continents, and prediction points back to the poles. So how good is our warning system right now? Honestly, thinner than most people would guess. We watch the sun almost entirely from one narrow band, the strip near its equator, because that's where Earth and nearly every spacecraft happen to sit. That view catches the storms already forming on the face turned toward us. What it can't do is tell us what's brewing underneath, in the machinery that decides when the next violent cycle ramps up. The trigger for that machinery sits near the poles, and the poles are exactly what we've never watched properly. Picture trying to forecast a hurricane season while only ever seeing the coastline, never the ocean where the storms are born. You'd catch each one late, with hours of warning instead of days. That's roughly where solar forecasting stands, guessing at the engine from the exhaust. And the cost of guessing keeps climbing. More satellites, more power grids, more aircraft crossing the poles on GPS, all of it exposed to a sun we can only half see. We know the missing piece. We know where it is. The frustrating part is that the fix isn't a mystery, it's a location we simply couldn't reach. Closing that gap was riding on a probe still years from its first good look. Think about what a magnetic field line actually does near the pole. Down at the equator, the sun spins fast, dragging its field into neat spirals. Up near the top, the rotation slows and the lines start to bunch, cross, and knot. That tangling isn't just messy, it's a place to hide energy. When field lines get twisted past a certain point, they don't relax quietly. They store tension like a wound spring, holding it until something gives. Then the lines snap into a simpler shape and dump that stored energy all at once. Physicists call the process magnetic reconnection, and it's the engine behind flares that release the equivalent of billions of megatons in minutes. The suspicion is that the poles are where this coiling runs deepest. If the field lines there are more sheared, more braided than anywhere else, they'd be the natural reservoir for the sun's most violent moments. Energy would build quietly at the top, out of sight, then travel outward once it broke free. For decades, that stayed a suspicion because nobody had watched a pole tangle in real time. You could model the twist, you couldn't confirm it. And that gap mattered, because if the poles are where the field tangles worst, they're where the sun's temper is set. So they built the poles out of math. Feed a supercomputer the equations for plasma, rotation, and magnetism, let it churn for weeks, and out comes a pole no human eye had ever seen. Swirling flows, buried field lines, the whole cap rendered in numbers. Different teams built different poles. One model showed the magnetic field concentrated in tight bundles near each cap. Another spread it into broad, smeared sheets. A third had material sinking at the poles like water down a drain, dragging the field with it. Each version behaved on its own terms. Each obeyed the physics its makers trusted most, and each disagreed with the others about what was actually up there, sometimes by a lot. That's the uncomfortable part. A simulation always gives you an answer, clean and confident, whether or not it's right. Without a real measurement, there was no way to tell the honest model from the one quietly fooling itself. For decades, the poles stayed a place you could only guess at, and the guesses kept multiplying. Physicists knew at least most of them had to be wrong. They just didn't know which. Every simulation made a prediction, and one spacecraft was about to grade them all. The disagreement came down to a picture nobody had ever seen. One camp argued the polar field stays orderly right through the flip, a single clean patch of magnetism that fades, weakens to nothing, then rebuilds with the opposite sign, smooth as a dimmer switch. In their models, the pole is calm even while the rest of the sun churns. The other camp said, forget the tidy version. To them, the reversal is a brawl, dozens of small magnetic patches drifting up from lower latitudes, some pointing north, some pointing south, cancelling and colliding until one polarity finally wins by a hair. In that world, the pole isn't a single field at all. It's a crowd. The two pictures predict wildly different things. A smooth pole flips fast and predictably. A chaotic pole can stall or briefly show two poles of the same sign at once, or flicker back and forth before it settles. And here's what made it maddening. Both ideas fit the data we already had, because all that data came from near the equator, looking at the pole almost edge-on. From that angle, a smooth field and a messy one can look nearly identical. The blur hid the difference. So the theories piled up, each internally consistent, each impossible to rule out from where we stood. Only a photograph from above could end the argument. And it wasn't just one puzzle waiting up there. Three of the biggest questions in solar physics all traced back to the same blind spot, the same patch of sky no camera had ever framed properly. Forecasting came first. Every prediction of the next cycle leaned on how fast magnetic flux drained toward the poles, and that drainage rate was exactly what we couldn't measure. Guess it wrong by a little, and a forecast years out drifts by a whole solar maximum. Then the corona. Why the outer atmosphere runs past 1 million degrees Celsius while the surface sits near 5,500 degrees Celsius stays unsolved, and the open field lines that might carry the answer fan out straight from the poles. We were reading the mechanism from the side, foreshortened, smeared. And the dynamo underneath it all, the engine that flips the field every 11 years, hinges on what the polar fields actually do at the turning point. Get those wrong, and the whole model of how the sun regenerates itself rests on a number nobody had confirmed. So the same few square degrees of sky, if we could just see them cleanly, might settle forecasting, heating, and the dynamo at once. One view, three answers. So much rode on so few pixels that no one had yet captured. Here's the part that made the whole thing feel like a gamble. The answers were sitting up there, waiting, but the only spacecraft built to read them wasn't in position yet. It was still climbing, tilting its orbit degree by degree, trading fuel and years for altitude above the sun's equator. And the sun wasn't waiting. Its magnetic cycle keeps its own schedule, roughly 11 years from one quiet stretch to the next, and the great reversal of its poles was creeping closer with every month. Miss the window, and you'd watch the flip you traveled 60 million kilometers to see happen while you were still looking at it edge-on. So the mission became a race against a clock nobody could pause. The spacecraft had to reach a high enough angle before the poles turned over, or the timing that justified the entire journey would slip away. Every orbit mattered. Every degree of tilt brought a slightly better look at ground no camera had ever framed. Down on Earth, all anyone could do was track the geometry, run the models, and wait for the vantage to arrive. The instruments were sound. The trajectory was set. The only thing left uncertain was whether the machine would be high enough in time. That climb began on a February night when a rocket lifted off toward the sun. It was February 10, 2020, at Cape Canaveral, and an Atlas V rocket carried Solar Orbiter into the dark. The spacecraft weighed about 1,800 kilograms, and packed inside were 10 instruments built by teams across Europe and the United States. This was a joint mission from the European Space Agency and NASA, years in the making. For a few minutes, the rocket did what rockets do, punching up through the atmosphere and shedding stages behind it. Then the upper stage lit again and pushed the probe onto a path that wouldn't loop back to Earth. Solar Orbiter was leaving for good, aimed at the inner solar system. And here's the strange part. To get closer to the Sun, you can't just point at it and fire. The Earth is already whipping around the Sun at roughly 30 kilometers per second, and the spacecraft carried all that sideways speed with it. To shed that momentum and drop inward, Solar Orbiter would have to trade speed with entire planets, swinging past them again and again to bend its orbit. The design goal was ambitious. It needed to climb out of the flat plane where every earlier probe had been stuck. But launch was only the first move in a slow gravitational dance lasting years. Solar Orbiter didn't punch straight for the Sun. It swung inward on a long, patient curve, trading speed and direction with planets instead of burning fuel it didn't have. Every pass was borrowed momentum, carefully timed. Venus did the heavy lifting. The spacecraft flew past it again and again, letting the planet's gravity bend its path a little more each time. One flyby dropped it closer to the Sun. The next started tipping the whole orbit sideways. Earth got one turn too, early on, a single flyby that set up the geometry for everything that followed. Miss the window by hours, and the whole sequence unravels. So the trajectory team threaded flyby after flyby, years apart, each one aimed within kilometers. This is the price of leaving the plane. You can't just point and go. The Sun's gravity keeps you flat, and the only way out is to steal a sideways kick from a passing world, then wait, then do it again. Each Venus encounter raised the tilt by a few more degrees. Slowly, the flat racetrack every probe before it had run started to lean. With each loop, the craft edged toward an angle no imager had ever held. Solar Orbiter didn't travel light. Bolted behind its heat shield sat 10 instruments, split into 2 camps. 6 of them look outward at the Sun itself, while 4 sense the space right around the craft, the fields and particles you can't photograph. That second group is the feeling half. Magnetometers read the strength and direction of the magnetic field threading past. Other sensors count the ions and electrons in the wind, clocking their speed and temperature as they stream by. This is the same kind of touch Ulysses had, a probe reaching out to measure what it passes through. But the first group is where everything changes. The extreme ultraviolet imager captures the corona in wavelengths our eyes can't see. The polarimetric and helioseismic imager maps the surface magnetic field directly, drawing the tangled lines as an actual picture. A coronagraph blocks the blinding disk so the faint outer atmosphere shows up around the edge. So this craft could do both at once. It could feel the Sun the way every earlier mission had, and it could stare straight at it. 6 sets of eyes, aimed at a face no camera had ever seen from above. This time, when the poles came into view, there would be pictures. But those eyes couldn't just hang out in the open. This close to the Sun, sunlight hits with a force that would cook any normal camera in seconds, so the instruments ride tucked behind a heat shield built to take the worst of it. The shield faces the Sun head-on and lets the delicate hardware hide in its shadow, a few degrees warm instead of hundreds. The trick is that a camera hiding in shadow can't see anything. So the designers cut small doors into the shield, little peepholes that swing open just long enough for the instruments to look, then close again before the heat wins. Every observation becomes a gamble against temperature, timed to the second. On the ground, all of that had been tested, modeled, rehearsed. Now it was millions of kilometers away, doing it for real, with no one able to reach out and fix a thing. The shield was holding, the doors were cycling, and the spacecraft kept falling inward, closer to the Sun than any camera had ridden before. As it neared the Sun, the doors opened, and the first close-ups came back stranger than expected. The very first images from Solar Orbiter's closest camera showed something nobody had catalogued before. Scattered across the surface, thousands of tiny bright flickers popped into view, each one flaring for a moment and fading. The scientists gave them a name that stuck. They called them campfires. These aren't like the giant flares that make headlines and knock out radios. A campfire spans maybe 400 to 4,000 kilometers across, small enough that only a camera riding within 77 million kilometers of the sun could resolve them at all. From Earth's distance, they'd smear into the background glow and vanish. But size can fool you. There are millions of these little sparks going off all over the sun at any given moment, blinking in the ultraviolet like embers in a fire pit. Each one is faint. Together, they add up to something that might matter enormously. And that's where they touched one of the oldest puzzles in solar physics. The surface sits near 5,500 degrees Celsius, yet the atmosphere above it, the corona, burns to over 1,000,000 degrees. Heat isn't supposed to flow that way, from cool to blistering hot. Something has to be pumping energy up there constantly. The campfires looked like they might be part of the answer. These miniature flares hinted the corona's furnace was lit by millions of small sparks, but from where? Solar Orbiter couldn't just fly over the sun's pole. Physics won't let you swing a spacecraft above the plane of the planets for free. Every orbit around our star sits stubbornly flat, and tilting it costs a staggering amount of energy, more than any rocket we build can spare. So the mission cheated, using gravity instead of fuel. Each time the craft swings past Venus, it steals a little of the planet's momentum and bends its own path higher above the ecliptic. One pass, then another, spaced years apart around the inner solar system. The launch orbit sat right in the plane, at 0 degrees. After the first Venus encounter, the tilt crept up to a modest angle. The next flyby nudged it higher, then the next. Each gravitational handshake ratcheting the inclination up by a few degrees at a time. It's slow, patient work. You can't rush an orbit that takes months to complete, and Venus only lines up on its own schedule. The spacecraft has to wait, loop, and return to the exact spot where the planet can give it another push. Degree by degree, the vantage point climbed away from the equator, toward latitudes no camera had ever seen up close. The craft was climbing a ladder, rung by rung, toward a view of the pole itself. By early 2025, the numbers finally crossed a line that mattered. Solar Orbiter's orbit had tilted past 17 degrees relative to the sun's equator, and every gravity assist from Venus was set to push that angle higher still. For decades, every spacecraft that watched the sun did it from more or less the same flat plane, staring at the equator dead on. That flat vantage point hides something. When you look at a sphere from the side, the top and bottom get squeezed into a thin, crowded sliver near the edge. Features near the poles pile up on each other, foreshortened into almost nothing. You can see that a pole exists, but you can't really read it. Now, degree by degree, that squeezed cap started to relax. The high latitudes that used to hug the rim began drifting inward, spreading out, gaining room to breathe. Structures that had always been edge-on smears were turning to face the cameras. The instruments were watching all of it happen in real time, banking every frame for the long trip back to Earth. We're holding those first tilted views for a moment, because what they showed deserves its own telling. For the first time, the sun's face began to tilt toward us, like a head slowly bowing. Solar Orbiter was climbing off the flat plane where every spacecraft before it had been stuck, and even a few degrees of tilt changed everything. From that new angle, regions that had always hidden near the top edge of the disk began to swing into clear view. The curve of the sun near 70 degrees latitude, once smeared into a thin sliver, started opening up into something you could actually study. By the time the orbit had tipped past 17 degrees, the difference was obvious in the raw frames. Areas that used to sit crushed against the limb, foreshortened into near-invisible lines, now spread out with real width and depth. The magnetic structures up there stopped being guesses and started being measurements. Every earlier telescope had looked at these latitudes edge-on, like trying to read a page held sideways. Tilting the whole spacecraft above the ecliptic did what no zoom or filter could. It let sunlight from the high latitudes arrive straight at the cameras instead of grazing past them. And this was still the shallow part of the climb. The craft hadn't reached its steepest angles, hadn't looked down on the true pole yet. What it caught here was the approach, the first honest slant onto ground that had been a blur for 4 centuries. It was a preview, and the preview alone rewrote what textbooks showed. But climbing higher took time, and time was the one thing the sun wasn't offering. The solar cycle runs on its own schedule, roughly 11 years from one quiet stretch to the next violent one, and it doesn't slow down for a spacecraft still gaining ground. The forecast pointed at 2024 to 2025 for solar maximum, the window when the star's magnetic field tears itself apart and rebuilds backward. That's the flip. North becomes south, south becomes north, and it happens fastest right over the poles the probe was still crawling toward. So the mission had a deadline nobody set on purpose. Each orbit nudged the viewing angle a little steeper, a few degrees at a time, and each pass around Venus was months apart. The steepest, most revealing look was still several loops away. Meanwhile, the sun was waking up. Sunspot counts were climbing, flares were coming harder, the whole face growing restless in a way that pointed straight at the peak. If the flip arrived before the craft got high enough, it would be watching the most important moment from the wrong seat, catching the aftermath instead of the act. The math was uncomfortably tight. The sun was heating toward its peak, and the probe was still gaining altitude. By 2024, the numbers left no doubt. The sunspot count climbed month after month, and the smoothed curve blew past the forecasts that experts had signed off on years earlier. The sun wasn't easing into its peak, it was slamming into it. Active regions bloomed across the disk, some wider than 10 Earths laid end to end. Where a quiet sun might show a handful of spots, observers were logging over 200 in a single count. The magnetic knots that drive these storms were tangling faster than the surface could smooth them out. Then the flares came. X-class eruptions, the strongest category we track, fired off in clusters, hurling billion-ton clouds of plasma into space. In May 2024, a barrage of them lit up auroras as far south as Mexico and drove the most intense geomagnetic storm in 20 years. Radio blackouts rolled across the daylit side of Earth. GPS signals wandered. Airlines rerouted flights away from the poles. From the ground, it looked like the sun had lost its temper all at once, throwing everything it had at the inner solar system. But all of that violence was happening near the equator, where the spots live and the flares ignite. The real story was unfolding somewhere the fireworks couldn't reach. While the surface raged, the poles were quietly beginning their great reversal. By early 2025, Solar Orbiter had spent years bending its orbit a little more with every pass by Venus. Each flyby tilted the path higher, trading speed for angle, until the spacecraft was riding 17 degrees above the plane the planets share. That doesn't sound like much, but it was enough to lift its gaze off the sun's midsection for the first time. From that height, the geometry finally worked. Instead of staring at the equator edge-on, the craft could look down and catch a sliver of the region no camera had ever properly framed. The South Pole was slipping into view, no longer foreshortened into a thin, useless smear at the bottom of the disk. And the timing was uncomfortable. The sun was climbing toward the peak of its cycle, the exact stretch when the polar fields weaken, collapse, and swap signs. The one place we'd never seen clearly was doing the one thing we least understood, and it was doing it right now, on a clock nobody could pause. So the mission pointed everything it had at that faint southern edge and waited for the light to be right. There was no rehearsal for this, no earlier picture to compare against. In March 2025, the craft turned its cameras toward the South Pole and started recording. Each instrument sat behind its own protective door, a shutter built to keep the worst of the heat off optics that cost years to grind and calibrate. Opening one at the wrong moment near the sun can cook a sensor in seconds, so the sequence was timed to the fraction. one door after another, each held until the craft confirmed it was pointed exactly where the plan said it should be. 10 instruments in the suite, and this time nearly all of them needed to look at once, the images to catch the surface and the atmosphere in ultraviolet and visible light, the spectrometers to read what the gas was made of and how fast it moved, the magnetograph to trace the field threading up out of the ground beneath the pole. One by one, the doors swung clear and the light poured in. The craft held its tilt, 17 degrees above the flat plane every telescope on Earth is stuck inside, and for the first time, the shots weren't glancing across a foreshortened rim. They were looking down toward the cap itself. For 17 degrees of hard-won angle, the sun's bottom edge rolled fully into view. Then came the part no engineer can rush. The images sat in solid-state memory aboard the spacecraft, tens of millions of kilometers out, waiting for a moment when the high-gain antenna could point back at Earth and open a link. Solar Orbiter doesn't stream in real time. It stores what it captures, then trickles it home whenever the geometry and the ground stations line up. The data rate this far out is thin, a few tens of kilobits per second on a good pass, so a single high-resolution frame doesn't just arrive. It bleeds back byte by byte. The signal itself moves at the speed of light, but light needs minutes to cross that gap, and the full download stretched across pass after pass on ESA's deep space dishes in Argentina, Spain, and Australia. A pointing so hard-won that it cost a decade of gravity assists, now hinged on antennas turning at the right hour, weather over the ground stations, and a queue of other missions sharing the same ears. On the ground, the team knew exactly what should be sitting in that buffer. They just couldn't see it yet. Every hour of silence was another hour the first true look at a solar pole existed, only as ones and zeros somewhere in transit. The signal took days to arrive, and when it did, the room fell silent. The frames loaded line by line, and there it was. The sun's south pole, seen straight on for the first time in human history. Not a smeared edge glimpsed across 93 million miles, not a sliver fighting the foreshortening, but the cap itself, filling the view. Solar Orbiter had climbed to about 17 degrees below the equator by early 2025, enough tilt to tip the pole into full sight. The images came from March, downlinked over the following weeks, and released that June. 400 years of watching the sun, and nobody had ever owned a picture like this. You could see the granulation, that endless boil of plasma cells, each roughly the size of Texas, wrapping right over the curve of the pole. The chromosphere glowed in ultraviolet, threads of gas at hundreds of thousands of degrees, arcing across a region no telescope on Earth had ever resolved this cleanly. 3 instruments stared at once, one mapping visible light, one reading the magnetic field, one catching the million-degree corona layered above. Together, they built something no single Ulysses pass could ever manage, an actual portrait instead of a graph of numbers. The detail was staggering, sharper than anyone had let themselves hope for. And then the science team looked closer at the field data. The pictures were beautiful, and the magnetic map beneath them made no sense. A magnetogram is supposed to be simple to read at the poles. One color for positive polarity, the other for negative, a clean patch of field pointing steadily in or steadily out. That's what a stable pole looks like, and it's what every model on the wall predicted the team would find. So they pulled up the polar data, expecting one dominant sign, one uniform sheet of magnetism anchoring the top of the star. Instead, the readout came back mottled. Patches of opposite polarity sat side by side, tangled together where there should have been calm. At first, the obvious suspect was the instrument. Maybe a calibration drift, maybe noise creeping in at the edge of the disk where the geometry gets awkward. They ran the checks. The signal held. The mess was real, and it was strong enough that no rounding error could explain it away. That left the uncomfortable option, the one nobody says out loud until the numbers force it. The field near the pole wasn't behaving like a single settled cap at all. Both readings were showing up in the same place, at full strength, refusing to cancel. Whatever this was, it wasn't in the textbook picture of a quiet, one-sign pole. Both of the sun's magnetic polarities were sitting at the same pole at once. So the team did what you do when the data breaks the model. They checked the instruments. Every calibration curve, every pointing log, every temperature reading from behind the heat shield came back clean. The spacecraft was working exactly as designed, which meant the signal was real. Both magnetic signs, north and south polarity, sitting at the same pole, holding steady across pass after pass. Nobody had a slide for this. The graphs coming off the downlink didn't match anything in 4 centuries of solar observation. For a few weeks, the reading just sat there, stubborn and unexplained. Researchers pulled the raw magnetograms into every model they had. They stacked the polar field measurements against the sunspot record, against the timing of the cycle, against what the equator was doing at that exact moment. And slowly, as the numbers lined up, a shape started to form. The timing wasn't random. It matched something the equatorial data had been hinting at for years, a moment the whole 11-year rhythm builds toward, but nobody had ever caught from overhead. Then it clicked. What they were looking at wasn't a mess. It was a snapshot of the sun turning itself inside out. Look at what the pole actually showed. Not the clean single polarity you'd draw on a diagram, one color for north, one for south, tidy as a bar magnet. The field up there was split, patches of positive and negative sitting side by side, crowding each other for room. That's the tangle. During the quiet years, the poles hold one dominant sign, negative at the top, positive at the bottom, or the reverse. But in these frames, the dominant sign was breaking apart, old polarity fading, while the opposite crept in from below, both of them fighting for the same ground at once. This is exactly the thing the cold open promised you. Every textbook picture of the sun's poles is a still frame, frozen at one moment in the cycle, and it's wrong the instant you look during the changeover. The real pole isn't a fixed cap of magnetism. It's a place where the whole star's field rebuilds itself. So the map we started with, the neat one, was a lie of timing. Catch the sun on the wrong year, and the poles don't match the drawing at all. Here it was, mid-transition, north and south polarity braided together in a single view nobody had ever recorded from above. Seeing the flip in progress answered one question and detonated a dozen more. For decades, we'd inferred the polarity flip from indirect signs, tracking sunspots at low latitudes and guessing at what the poles were doing from millions of kilometers off to the side. Solar Orbiter changed that by tilting its orbit above the ecliptic and looking straight down at the magnetic field where it actually lives. What it recorded wasn't a snapshot of before and after. It was the reversal caught in motion. The instruments watched patches of one polarity fade while the opposite sign crept up from lower latitudes, weakening the old field and slowly overwriting it. At solar maximum, the poles don't simply switch overnight. They pass through a messy stretch where both signs coexist, the net field near zero, before the new orientation locks in. Nobody had ever measured that muddle from a proper vantage point, only modeled it and hoped. Now the model had a face. The braided, contradictory field the theorists had sketched turned out to be real, and it was reorganizing itself frame by frame in the downlinked data. Every 11 years the sun does this, and for the first time a spacecraft was overhead to witness the changeover as it unfolded. That mattered for more than a pretty measurement. The polar field at the end of one cycle is the seed of the next, the quantity forecasters most want and least understand. Watching it flip meant we could finally learn to see it coming. Here's what Solar Orbiter actually saw when it looked down at the pole. Not a clean magnet with a single north and a single south, but a patchwork. Regions of positive polarity sitting right beside regions of negative, jostling across the same stretch of surface. For decades, the sun's poles carried one clear sign each, the way a bar magnet does. During the flip, that clarity dissolves. The old field doesn't fade evenly. It breaks into fragments, and those fragments drift and cancel against patches of the opposite sign, creeping up from lower latitudes. So for a stretch, the pole holds both charges at once. The strength of the overall polar field drops towards zero, not because nothing's there, but because the pluses and minuses are busy erasing each other. It's less a switch being thrown and more a slow, churning trade. And underneath the cancellation, the replacement is already arriving. Fresh flux of the reversed sign migrates poleward, gathering, waiting to become the next cycle's dominant field. For a while, the two coexist in the same crowded space, the departing and the incoming layered together. Solar Orbiter caught this from above, watching the mixed field in real time rather than guessing at it from the side. This tangled state is fleeting, and catching it was a matter of arriving at the perfect moment. For decades, the pole during reversal was a coin toss between rival models, each running on a different guess about how the field behaves up there. Some codes predicted a tidy handover, one polarity fading as the other rose in orderly fashion. Others painted the pole as a mess of scattered patches fighting for dominance. Nobody could check them, because nobody had looked. The pictures settled it in one direction fast. What Solar Orbiter saw over the South Pole wasn't smooth at all. It was fragmented, chaotic, dozens of small magnetic regions of both signs crowded together with no clean boundary between them. That single observation acts like a filter. Any model that assumed a gentle, symmetric flip has a problem, because the real pole was ragged and contradictory right when the theory needed it to be calm. The measured field strengths and the sheer patchiness didn't match the neat curves that had looked so convincing on paper. So the modelers started comparing, line by line, prediction against photograph. Some had built in enough turbulence and small-scale structure to survive the comparison. Others, elegant as they were, simply didn't describe the sun that showed up in the data. Some simulations were vindicated, and others collapsed on contact with reality. But the images were only half the story. Solar Orbiter didn't just photograph the poles, it carried instruments that tasted the particles streaming off them, measuring the speed and composition of the plasma pouring into space. When the team lined up the pictures with those wind readings, the two datasets locked together like a key finding its lock. The fast solar wind, that torrent moving near 750 kilometers per sec, traced straight back to the polar regions the cameras were now staring at. Down at the equator, the wind was slower, denser, tangled. Up high, it was clean and quick, and the source was no longer a guess pieced together from stray measurements. It was right there in the frame. 30 years earlier, Ulysses had flown blind over those same latitudes and felt this exact wind rushing past its sensors, faster than anyone expected, with no eyes to see where it came from. It recorded the pulse without ever seeing the heart. Now that heart was on screen, and the numbers lined up. Two spacecraft, 2 generations apart, describing the identical physics from opposite ends of the problem. One had touched the wind and wondered. The other looked up and answered. The picture Ulysses couldn't take finally matched the pulse it once recorded. Now the corona had a witness looking straight down its throat. From above the pole, Solar Orbiter watched those tiny bursts of heat the mission had nicknamed campfires, flickering across the surface at scales just a few hundred kilometers wide. Down at the equator, they'd looked like noise. From up here, they lined up with something. The polar field, it turned out, wasn't a tangle. Great stretches of it reached straight out into space instead of looping back, open lines fleeing the sun with nothing to catch them. And every one of those open lines traced back to the same places the fast wind was pouring from at over 700 kilometers per second. So the pieces started clicking into a chain. Millions of campfires dumping heat into the base of the corona, open field lines standing ready above the poles like chimneys, and the fast wind roaring out along exactly those paths, carrying the energy away. For decades, the coronal heating problem sat there as a paradox, a surface at 5,500 degrees Celsius somehow wrapped in an atmosphere over 1,000,000 degrees hotter. From the pole, you could finally see where the extra energy was going in. The furnace was being lit at the poles, exactly where we'd been unable to watch. Here's what that direct view changed. For years, the single best predictor of how strong the next solar cycle would be was the strength of the sun's polar magnetic field at minimum. Weak poles now, weak cycle later. Strong poles now, a fierce one coming. The trouble was, we'd never actually measured that field head-on. We inferred it, squinting at the pole's edge-on from down near the equator, extrapolating across the most foreshortened, distorted patch of the whole disk. It was a forecast built on a guess about the one number that mattered most. From above the pole, that guess became a reading. The magnetograph could stare straight down the field lines and count the true polar flux. No projection, no correction, no assumption stacked on assumption. The precursor everybody had been leaning on for decades finally had a real value behind it. And the dynamo models drank it up. Feed them a measured polar field instead of an estimated one, and the spread of possible futures narrows. The confidence tightens. The next cycle's shape comes into focus earlier than the old methods ever allowed. For the first time, the best clue to the sun's future was no longer a guess. So why does one flipped field matter this much? Because the polar field at solar minimum is the seed. The strength of that quiet magnetic reservoir at the sun's caps sets how violent the next 11-year cycle will grow. Measure the seed, and you've measured the harvest before it sprouts. That's the anchor the dynamo was missing. Deep inside the sun, rotating plasma stretches and wins magnetic field like a spring being loaded. The reversal is the moment that spring resets, poles wiped clean and rebuilt with the opposite sign, ready to coil up all over again. Catch that reset precisely, and you can time the whole machine. Not a vague window of a few years, but a genuine forecast of when the next maximum arrives, and roughly how fierce it runs. The old approach waited for spots to pile up and guessed backward. This one reads the starting conditions directly. Every sunspot, every flare, every eruption that will ever leave this star over the coming decade traces back to that buried, resetting field. The flip isn't a footnote in the cycle. It's the pivot the entire rhythm turns on. Understanding the flip is understanding the clock that governs every storm headed our way. So Solar Orbiter didn't just capture one image and call it done, it layered them. 6 instruments, all aimed at the same patch of sky beneath the sun, each reading a different signature of the same fire. The polarimetric and helioseismic imager mapped the magnetic field, showing exactly where the polarity clustered and where it scattered. The extreme ultraviolet imager caught the corona glowing at temperatures near 1 million degrees Celsius, and Spice broke the light into its chemical fingerprints, tracing which elements sat where in the atmosphere above the pole. Stack those together, and you get something no telescope on Earth or in orbit near the equator had ever produced. A view of the solar pole in visible light, ultraviolet, and magnetism at once, all from a vantage tilted 17 degrees below the equator. The magnetic patchwork lined up with the ultraviolet hotspots. The chemical map matched the field structure underneath it. Each dataset confirmed the others, and the picture snapped into focus, coherent from every angle they could measure. For the first time, one region of the sun long guessed at was simply being seen, in full, cross-checked, and undeniable. And this was only the South Pole. The craft is still climbing to look at the north. So go back to that first image, the one that opened all of this. A sun that refused to sit still on any map we drew, poles that behaved like nothing our flat, edge-on view could explain. Now we can name what we were looking at. We were staring at a star in the middle of turning itself inside out. The messy magnetism at the South Pole, the tangle that broke every clean model, that wasn't an error in the data. It was the reversal itself, caught in motion. The field that should have pointed one clean direction was scrambled because it was actively flipping, north becoming south, the whole magnetic order of the sun rebuilding from the poles down. That's the answer to the wrong map. For 4 centuries we drew the sun from the side and quietly left the top and bottom blank, filling them with guesses because no one had ever looked. The blank spaces weren't empty. They were where the sun did its most important work, hidden by nothing more than the angle we happened to view it from. And now we'd measured it, directly, with instruments pointed straight down at a solar pole for the first time. No inference, no model standing in for a photograph. The silence in that control room was the sound of a 400-year blind spot closing. So here's what sits directly above and below the sun. Not a smooth cap, not a tidy mirror of the equator, but a churning, tangled mess of magnetism. The polar regions are where the sun's field lines break open and stream outward, unanchored, pouring charged particles into space at over 700 kilometers per second. These are the launch pads for the fast solar wind. The open field lines don't loop back down like they do near the equator. They reach out and keep going, past the planets, past Pluto, all the way to the edge of the heliosphere where the sun's influence finally fades. And the poles don't stay put. Every 11 years or so, they swap. North becomes south, south becomes north, and the entire magnetic architecture of the star turns itself inside out. We'd theorized that flip for decades. Now we've watched it from directly overhead, the one vantage point that had eluded us since Galileo first sketched sunspots. The blind spot is closed. The map has a top and a bottom at last. Chaotic, open, flipping poles that drive the wind we've felt for a lifetime and never once seen from above. But even this triumph left the sun holding cards we haven't seen. So far, everything we've seen belongs to the south. Solar orbiter tilted just enough to catch the underside of the sun, and that first glimpse rewrote the map. But a sphere has two ends, and the northern cap is still dark to us, still unphotographed, still waiting. The spacecraft isn't done climbing. Each pass by Venus kicks the orbit steeper, and over the next few years that angle keeps rising, from 17 degrees toward 33 degrees and beyond. Higher tilt means a longer, cleaner look, and it means finally swinging the cameras over the top of the star instead of the bottom. The north isn't a copy of the south we can assume by symmetry. The sun is messy. Its two hemispheres don't always keep the same pace, and sunspot counts have drifted apart between north and south before. What holds true below the equator might not hold true above it. There's a reason this matters more than filling in a blank on a chart. The magnetic reversal we've talked about happens across the whole sun, and nobody has ever watched both caps turn over at the same time from a clear vantage. Whether the two poles flip in lockstep is a question still hanging in space. So here's what happens next. Solar orbiter isn't done bending its path. Every time it swings past Venus, the planet's gravity does the heavy lifting, tilting the orbit steeper against the plane where all the planets ride. The spacecraft can't climb on fuel alone, so it borrows Venus over and over. The first tilt got it to roughly 17 degrees above the equator, high enough for that first honest glimpse of a pole. But the plan doesn't stop there. Later gravity assists are set to push the inclination past 24 degrees, then toward 33 degrees in the years that follow. Each notch higher means the camera looks down on the cap instead of squinting across it. That angle is everything. From 17 degrees, the pole still sits near the edge of the disk, foreshortened, half hidden by the sun's own curve. Climb another 10 or 15 degrees, and the same region opens up, flattening out under the instruments so the magnetic field and the churning plasma below read cleaner. It's a slow build, measured in years and looping Venus encounters, not a single dramatic leap. But the trajectory is already drawn. The sun's poles, blank on our maps for 4 centuries, are about to come into steadier focus, one orbit at a time. Each future pass promises a sharper look at a region we only just met. So step back and look at what we've actually been circling. The sun we grew up drawing, that steady yellow disk pinned to the sky, turns out to be something far stranger. It breathes, it churns, and roughly every 11 years, it turns its own magnetism inside out. Think about what that means. A ball of plasma, 1.3 million times the volume of Earth, swaps its north and south magnetic poles, then does it again and again, like a heartbeat measured in decades. The surface we once called calm is a shifting field of loops and knots, snapping and reconnecting, throwing heat and matter outward at speeds we're still learning to predict. Parker Solar Probe felt that violence from the inside. Solar Orbiter is now watching the poles reorganize from above. 2 spacecraft, 2 vantage points, one restless machine that never actually sits still. This isn't a lamp hanging in the dark. It's an engine, winding and unwinding its field on a rhythm older than any human record, driving a wind that fills the entire solar system. That living, flipping star is not a distant curiosity, it reaches all the way to your pocket. Think about what runs through that pocket: the satellite pinging your phone's location, the timing signal that keeps card payments honest, the GPS guiding a plane onto a runway. All of it depends on a fleet of spacecraft flying through the sun's outstretched field, and when that field lashes out, those satellites take the hit. A strong solar storm can swell the upper atmosphere, dragging low-orbit satellites down faster and scrambling the drag models that keep them from colliding. In February 2022, one geomagnetic storm knocked out 38 of 49 Starlink satellites SpaceX had just launched. The radiation that comes with these events also fries electronics and forces astronauts on the space station to shelter in shielded modules. Down on the ground, the same storms push currents through power lines that were never built to carry them. In 1989, a solar storm collapsed the Quebec grid in under 90 seconds, leaving 6 million people in the dark on a March morning. The bigger the storm, the wider the blackout, and the harder it is to bring back. Here's where the poles come in. The magnetic knots that hurl these storms outward are wound up by the same dynamo that flips the field at the poles. Watch the flip closely enough, and you start to see the storms coming from further out. The better we read the poles, the more warning we get before the next storm arrives. Think about what an extra hour of warning actually buys. Grid operators can drop transformers offline, reroute power, and lower the load on the lines most likely to fry when a geomagnetic surge rolls in. Those big transformers can take months to replace, and a single one can cost tens of millions. A heads-up turns a regional catastrophe into a scheduled inconvenience. The same forecast reaches the cockpit. During strong solar storms, radiation at cruising altitude climbs, and radio signals near the poles can drop out entirely. Airlines already reroute polar flights when the sun acts up, adding fuel and time. Better lead times mean fewer scrambled diversions and more flights that stay on their planned path. Pipeline operators watch too, since the same currents that stress power lines also creep into long metal pipes and speed up corrosion. Satellite teams can safe their spacecraft, tucking sensitive electronics away before the particles hit. Every one of these moves depends on knowing what's coming and how soon. Reading the poles feeds all of it. A clearer picture of how the field winds up and lets go sharpens the models that turn a distant flare into a local timeline. The forecast stops being a vague alert and starts being a plan. Every improved forecast is a blackout that never happens and a flight that lands safely. Solar Orbiter isn't finished. The spacecraft that just gave us our first real look at the poles is still climbing, and every pass around the sun nudges its orbit higher above the equator. What it saw at 17 degrees was only the opening move. The plan calls for the tilt to keep steepening through repeated flybys of Venus, each one borrowing a little of the planet's gravity to lift the viewing angle further. By the late 2020s, the orbit reaches past 30 degrees, and later still, it's designed to push toward 33 degrees and beyond. Higher tilt means a longer, steadier stare straight down onto the polar caps instead of a fleeting glimpse across the curve. That matters because the sun doesn't hold still. The magnetic cycle keeps turning. The flip we watched won't be the last, and a mission that lives across those years can catch the poles in different moods, not just one frozen frame. Repeat visits are how a single snapshot becomes a record. There's fuel budgeted, instruments still healthy, and a schedule of encounters stretching out ahead. Each orbit adds another band of data from a vantage point no camera held before. The story of the poles is still being written in the years of orbit left to fly. Two spacecraft, 2 decades apart, answered the same question in completely different ways. Ulysses flew blind across the poles in the mid-1990s, then again a few years later, carrying no camera capable of seeing the surface it crossed. It measured the wind, the magnetic field, the particles streaming past its hull, and from those readings we inferred a sun we could never quite picture. It felt the fast wind pouring off the poles at roughly 750 kilometers per second. It sensed the field lines opening outward, but it worked in the dark, translating force into numbers, never once looking down at the caps beneath it. Solar Orbiter picked up where that mission left its silence. It climbed above the ecliptic on Venus gravity assists, then tilted its cameras down and did the thing Ulysses never could. It brought back the first true images of the solar poles, the churning plasma, the tangled field mid-reversal, a face that had stayed hidden for 4 centuries of telescopes. One mission ended in 2009, its signal fading as the fuel line froze. The other is still flying, still climbing, still sending pictures home. Between a spacecraft that touched the dark and one that finally brought light, a blind spot became a portrait. Think back to where this started. For 4 centuries, everyone who looked at the sun looked at it from the side, along the same flat plane, watching sunspots crawl across a face that never once showed us its top or bottom. We drew maps of a star and left 2 blank circles where the poles should be. Then came the questions we couldn't answer from that angle. How the magnetic field flips every 11 years, why the corona burns hotter than the surface below it, where the fast solar wind pours out. Every one of those puzzles had a piece hiding at the poles, and we kept guessing at it with math instead of eyes. Getting above that plane cost a trip to Jupiter and a gravity slingshot just to bend the path upward. Ulysses felt the poles without ever photographing them, then went quiet in 2009. Parker dove closer than anything before, but stayed low, stayed flat. And in 2025, after all of it, a camera finally sat high enough to stare straight down at the churning cap and catch the field mid-flip, live, the reversal we'd only ever inferred. The blind spot closed, which leaves just one thing left to say about where all of this stands. So here's where we actually are. In 2025, for the first time in the whole history of looking up, we have clear images of the sun's south pole. Not a guess pieced together from the edges, an actual view taken from above the plane the planets sit in. Solar Orbiter tilted its orbit to about 17 degrees below the equator and looked back at the bottom of the star. What it caught was the pole mid-argument with itself, north and south magnetism tangled in the same place, exactly the mess you'd expect when the field is halfway through flipping. That flip isn't a theory anymore. We watched it happening at the cap, live, instead of reading it off sunspots months after the fact. The blind spot we'd carried for centuries is, for the south, just gone. The north is still coming. The spacecraft keeps nudging its tilt higher with each pass, aiming for around 33 degrees later this decade, and the top of the sun hasn't been seen straight on yet. It's on the way, not in hand. So that's the state of it. One pole imaged, one pole pending, a reversal caught in the act, and a machine still climbing to finish the job. If you want to follow the north when it arrives, the rest of the channel's right here.